Thanks for the introduction. I'm going to talk today about sort of a long-running project that I have been involved in. So this is work with my collaborators in the Environmental Health and Engineering Department, and it's kind of centered around improving knowledge of air quality in Baltimore, which historically didn't have a lot of spatially resolved knowledge about air quality. And it has kind of branched out from like one kind of a statistical problem to like many different projects that we're working on. I'm trying to give a flavor sampling of some of the projects. So just the three main things that I'm going to talk about. The first one is what the project sort of started with, is kind of mapping fine particulate matter in Baltimore using low-cost sensors. Then for the last 1.5 years or so, we have been focused on a particular neighborhood in Baltimore called Curtis Bay, which is a sort of has a heavy industrial presence along with a densely populated community, and so air pollution is a very significant concern there. And we'll talk about sort of how to understand sources of air pollution in Curtis Bay. And then, time permitting, I'll briefly talk about some of more foundational work about doing machine learning for spatially and temporally correlated data. So the air pollution mapping in Baltimore, as I said, is a long-running project with many collaborators. I'd like to highlight Claire, who was my PhD student, who led much of the work, and Kirsten is my main collaborator at Hopkins in environmental health and engineering. So the motivation for the work kind of stems from this picture. This is a typical picture you'll get if you go to airnow.gov, type the zip code for any neighborhood in Baltimore and pull up the map. You will get something like this. You can see that in the entire area, not just Baltimore, but around, there are 4 monitors. In the Baltimore city proper, you have just one monitor that measures fine particulate matter, and there is one just outside of the city on the eastern side that also measures particulate matter. Historically, it only measured once every 6 days. They have only very recently put an hourly monitor there. So this is what we get from the monitoring that is done by the Maryland Department of the Environment. So within the city, essentially, there is a single site. It used to be in a sort of heavily trafficked center at Old Town. Now they've moved it to a lake, close to a lake in the middle of a park at Lake Montebello. So I'm not sure how representative that measurement is for the city as well. But either way, you can see that with this sort of reference measurements, you don't get any information about how air quality varies within the city. So that's where the low-cost sensors come in, and this was developed as a part of SEARCH, which was an EPA-funded center. So one of the main projects of SEARCH was to build a low-cost sensor network in Baltimore, and this has been operating since late 2018. Kirsten was the PI for this, and I've been involved in the statistical analysis of the data since then. So these are the locations where there are now search monitors in Baltimore. The red dots are the low-cost sensor networks. The purple squares are the 2 reference monitors. And the search sensors measure a bunch of pollutants: fine PM, coarse PM, ozone, NO, NO2, carbon monoxide, methane. They also measure temperature and relative humidity. So we get a lot more measurements from these low-cost sensors. But there is no free lunch. Low-cost sensors are low cost for a reason. So if you look at the data quality, you would understand what are some of the problems of low-cost sensors. So these are what we did was we co-located a couple of sensors at the same site where there was a reference sensor to understand how biased the low-cost sensors are. And we could see, so the orange line is the MDE reference sensor. The green line is the raw low-cost sensor data, and the cyan line is the one that has gone through a sort of a preliminary calibration based on lab experiments. So that's the basic relative humidity temperature correction. So you can see that the raw measurements significantly overestimate the concentrations, but even after the lab correction, we are still overestimating quite a bit. So even after the lab correction, this is not the data that you can use in downstream analysis. It's highly inaccurate. So our first sort of analysis or stab at improving the data was to do a sort of a basic regression-based calibration of the low-cost data. So as we said, that the low-cost sensors were co-located with the reference devices, and we did a very basic linear regression, regressing the reference PM data on the low-cost data and some covariates, which is like relative humidity and temperature. So again, this is like extremely simple linear regression. The advantage of this is once you estimate these parameters from this co-located data, then at any location where you only have the low-cost sensor data, you can just plug in the estimated values of these parameters and predict the reference data. Okay, so this model was trained using data at Old Town, which was the site of the reference data at that time point. So this is sort of the test performance of our model. So our model is like the violet line. As you can see that for the most part, it tracks the orange line of the MD sensor data very well. And this is out of sample. We didn't use any of this data for training of the model. And this regression calibration is really, at that time, the state of the art for correcting low-cost sensor data. The type of regression varies. Some people use linear regression, some people use machine learning models, but regression calibration used to be, and in many ways still is, the state of the art. So we were happy with this performance, and we ran it for like 2-3 years, and it was reasonably robust. And so this was sort of the initial work that we did. Then we slowly, as we kind of evaluated the method over time, slowly a pattern sort of emerged, and this is kind of encapsulated here. So for most days, the air quality in Baltimore is generally good. And so it's like the concentrations are low, and our model does very well. We don't get that many days of a lot of air quality spikes. But whenever we got one, and this is an example, this is from 2019, December 23rd, the air quality went up to around 40 microgram per meter cube. And we saw that, yeah, our model also predicted the spike, but not as sharply as it should have. And at that point, we didn't pay too much attention to it because it was just one off day. But as we kind of kept collecting data and kept getting these occasional spikes in true concentrations, many of the times we found that our model is underestimating the spikes. It's doing very well at sort of the baseline levels. And this is sort of encapsulated here, which is a classification of the true air quality index and the model predicted air quality index. So when the true index was good, the model was also predicting good 96% of time. But when the true index was moderate or unhealthy, the model was predicting moderate or unhealthy only 75%. So 1 in every 4 spikes were being missed. And this is kind of problematic because I think one of the main utilizations of these low-cost sensors is to kind of understand when there is spikes locally in space and time. So if we're missing out spikes, that's kind of beating one of the main purposes of these low-cost sensors. So sort of the follow-up work, which was led by Claire, kind of went into investigating what is going on. Is this a data issue? Is this a bug in the code? Is this a fundamental model issue? And so on.
Let me ask you a question.
Yeah.
It looks like it's 2 or 3 days. Was there something happened on those days?
We don't know what happened, but it was a citywide spike. So it was not something very local, so somewhat regional, possibly. Yeah.
You also have the raw data from sensors. So what value did I?
The raw data overestimates a lot. Yes. And it gives you spikes also on days where there is not a spike. So we tried to understand this a little bit more from sort of a basic mathematical perspective. So let's revisit what we were doing. So this was our calibration model. We were regressing our reference data on the low-cost data and the covariates. We then tried to understand what is the property of this calibration model, and we kind of unearthed this thing that if we have the predicted reference levels, which we denote by y hat, then you can actually show that the true concentrations and the residuals, which is like the true minus the predicted, they are negatively correlated. What does this mean? It means that you get a plot like this, where these are the true concentrations and these are the residuals. So you can see that when the true concentrations are very high, the residuals are highly negative, which means your model is under-predicting quite a bit. So you can clearly see this, and this was not an artifact of the data or anything. This is a fundamental property of this regression calibration model. And so once we understood why this was happening, we thought this is not an ideal quality, because then we are kind of sort of mathematically guaranteed to under-predict peaks, which is definitely not what we want. The fix to this was surprisingly simple. We just switched the roles of the low-cost data and the reference data. So we previously had the reference data on the left-hand side, because that's the quantity we have to predict. So that's why we had it on the left-hand side. So it's somewhat counterintuitive to switch it, but we did switch it, and there are two reasons for that. One is sort of the more of an intuition that it is more organic to have the low-cost data X as a noisy version of the true measurement at that site, because the low-cost data is a biased and noisy version. So this model, sort of from an understanding of that low-cost data is more noisy, makes sense. The second fact is more mathematical, is that the negative correlation that we had when predicting the reference levels vanishes when we use the inverse regression model. You can actually show that the quality of the model fit is independent of the concentration. It tends to do well both at high concentrations and at low concentrations. Yeah.
Is there something here that the high sensors don't have measurement error?
Oh, the reference sensors, they will also have some degree of measurement error, but compared to what the low-cost sensors have, they're like orders of magnitude smaller. So it's all, yeah, for our analysis purposes, we assume it to be zero. They are the highest quality measurements you can get. So
this is like a following from like errors in variables.
Yes, yeah, errors. It's kind of errors in variables. It's also that at other locations, you will not have the reference data, so you'll only have the low-cost data. So we have to use that to get to the reference measurement. So that was one problem of the regression calibration that we can solve using the inverse regression. There was a second problem, and that was the regression calibration was kind of spatially unaware, in the sense that it doesn't use any information that air pollution at nearby places would tend to be similar, and that's kind of one of the bases for doing spatial modeling, that we model this correlation, and that is not being done. What regression calibration does is that, suppose this is the co-located site, it will train the regression calibration model, then it will apply it at every other site, at every other time point, without kind of using the available reference data at that time point, or even leveraging the correlation between nearby monitors. So that is also not ideal, because we know there is spatial correlation in air quality measurements. So for that, we use a very standard model for modeling spatial correlation, which is Gaussian processes. And to sort of briefly explain Gaussian processes, instead of considering this schematic where there is a bunch of low-cost sensors and maybe one or two reference sensors, consider this hypothetical schematic where there is only reference sensors. So we don't have to worry about measurement error. All of the locations had very high quality data, and we just wanted to create a map from that data, right? In that case, Gaussian process is an ideal model. We will simply model this, the reference measurements is a Gaussian process. It's essentially a normal distribution with some mean, and you can model the mean using land use variables and sort of day of the hour of the day, month of the year, kind of periodicity variables, and so on. And you can put the rest of the spatial correlation in the covariance. It's very simple to estimate the parameters. You can predict at any new location using basically conditional distributions, which are called kriging. And you can also get not only point estimates, but also uncertainty estimates. So if we had reference data at all these sites, we know how to deal with this problem. We have a very good sort of time-tested model. And this would probably how a map would look that interpolates through the data. But we don't have that. We have something like this. So our solution is simple. We still have the Gaussian process model, except that this y is not observed at most places except 1 or 2. And then for the other locations, we have the model for the low-cost data that sits on top of the Gaussian process model. So now we have a two-stage model, the Gaussian process model for the latent reference concentrations, and the observation model for the noisy low-cost data. So this is very similar to what a Kalman filtering does. A Kalman filtering has a true state space model. That state space is in time. Our state space is in space. And then you have an observation model for noisy sensor observations. So this is just a Kalman filtering in space. So we call it Gaussian process filter. And later we found out that there is now an EPA-approved calibration equation for Purple Air Network, which is a US-wide citizen science network. And their equation was also derived from an inverse regression model. They didn't use the Gaussian process part, but they also used the inverse regression model. They don't explain why they did it, but probably they saw the similar underestimation of the forward regression, and that's why they switched to the inverse regression. So that's our model setup, very simple, linear regression for the low-cost observations, and then a Gaussian process for the latent reference considerations. Some performance evaluation on holdout data. So as we said, there is one site outside of the city in Baltimore, which at that time used to give measurements every 6 days. So we compared our method with the regression calibration for December, when there was spike on one of the days. And you can see in terms of RMSE, our method does much better. But also if you look at particular performance on each of the days, you can see that for the days where the air quality was good, both models kind of does similarly well. But then that December 23rd, when the air quality spiked, our model correctly captured the spike that is not captured by the regression calibration model. So this is a map produced by the two methods on December 23rd. And as you can see that the sort of the elevated levels were not being picked up by the regression calibration, which was being consistently picked up GP filter. And we have now extended it to use two low-cost sensor networks. So there is the search network, which is a research purpose network. There's also the Purple Air network that's present in Baltimore. So if you go to Google Maps and look up air quality, you will get a number. And if you kind of keep zooming in, and you'll eventually go to a sensor, and that's usually a Purple Air sensor. And so Purple Air sensors are in throughout US. So we have a bunch of them in Baltimore as well. So we wanted to use that data. But one major difference between the Purple Air and search is one is a research purpose network and one is citizen science. And there is preferential sampling in the citizen science in the sense that it's more common in more affluent neighborhoods where people can afford to buy them and put them on top of their houses. So we saw that we looked at Zillow prices of houses where there was a Purple Air versus houses close to where the search network was. And you can see that it is like Zillow for Purple Air has a very thick right tail with a lot of Purple Airs being in very expensive houses, especially compared to sort of the median house price in Baltimore is around 210,000, and you can see that the purple layer has a lot of them. That's very much over. Search also has some of it, but it's much less sparse than the purple layer. So purple layer usually has a strong preferential sampling issue. I don't know if Google Maps are accounting for it when they're creating the maps. It doesn't seem that they are. So the biases that we see in the purple layer are probably in the Google Map air quality that you're seeing. And methodologically, the extension is extremely simple. We now have two observation models, one for search, one for purple layer. Each observation model has their own network-specific bias and noise parameters, and then the underlying Gaussian process model for the true pollutant levels stay the same. You can pretty much implement it in the same way as the single network GP filter. And so these are some maps produced. So these are the two maps produced when you use one network at a time. So this is purple layer only, that's search only, and the third one is combining search and purple layer. And you can see that there was a spike at this part of the city, which was missed by purple layer because there were no monitors in that area. And that is picked up by search, and it's also picked up when you're modeling both search and purple layer. And these are the uncertainty interval widths. And if you have more data, it typically helps with your uncertainty. If the data are reasonably in agreement, and we do see that, we get much tighter interval estimates when we're using both networks together than we're using just one of them. Right, so that's this project of mapping air quality in Baltimore. This was the regression calibration paper. This was sort of the diagnosis of underestimation issue and fixing it using the GP filter. And then the multi-network GP filter is currently in archive. So once we had this multi-network GP filter and we have been running and it's been stable, we wanted to sort of make this product public. So we collaborated with the Data Science and AI Institute at Johns Hopkins, and we have been working with a team of software engineers here who are kind of taking the code and creating these maps as a public product. This work is led by my postdoc, Bora Jin. So we have this dashboard. Let me see if I can click on this. So this is the dashboard we have on air quality in Baltimore. So it gives you historical concentrations of PM2.5 for the city for the last 6 years, 2019 to 2025. And it has a bunch of features, but let me first, in most of the days, the map looks like this. It's very spatially flat. And that is very typical of Baltimore. But then there are some days where you do see strong gradients in the city. So let me pick up one such day. So this was February 22nd in 2022. Again, we don't know what happened in the northeast part of the city, but it clearly had a spike, and all of the monitors in the area, it was not like one bad monitor, picked up a spike for multiple of the pollutants. And you can see that in the mean map, you can see a stronger version of this in the 98th percentile map, and the air quality was really bad in that part of the city. So you can sort of go through the days and months, and you can find information about air quality. We also have a neighborhood level aggregate where you can kind of hover over each neighborhood and see, like, here the concentration is around 16. Now, if you go to overlay, the concentration is around 76. So you can see how different they are. There is also an analytics tab where you can go and look at the time series. So this is the blue line is the citywide average predicted by our network. The orange line is a single observation from the reference site. So you can see for the citywide average, they're not that different. But now if you search with overlay, you can see the spike coming in here. And that is not recorded by the reference monitor because it's far away from that neighborhood. So this is something that will never be captured by a single reference monitor in the city that we are picking up through the low-cost sensors. There are also like hour of the day maps. day of the week, and then overall quality, air quality index histograms. And then if you go to the calendar, you will get sort of this kind of calendar on what the air quality was on different days of the year. So for example, if you go to June of 2023, this was a time period where we got a lot of wildfire smoke from the Canadian wildfires, and you could actually smell the smoke in the air, and the air quality became like 250 microgram per meter cube. So you can sort of see, and then you can just click on the day and understand what was going on. So you can see like the entire city was around red. So yeah, so there are a lot of features. Currently, it's just a historical dashboard. We are working on making it into a real-time dashboard with an alert system. So hopefully by summer, that will be live. So this is based on this multi-network GP filtering work that we have done. Okay, so switching gears a little bit, now I would like to focus on a particular area of the city, which is Curtis Bay, as I said in the beginning. So this project is in collaboration with Chris Hinney and his team, and also Greg Sawtell, who is a sort of a community activist in Curtis Bay. And so just to give a little bit of a context, this is Curtis Bay, this is Baltimore, this is Curtis Bay. This is a zoomed-in figure of Curtis Bay, and it has around 60 to 70 industrial sources of air pollution. It's also a neighborhood that's quite heavily populated. And in particular, there is the CSX coal site, which manages a lot of coal in the area. And so you can see this mountain of coal just right across the children's park there. And you can see like every morning, if someone comes out and sort of rubs their hand on their car, they will get something like that. So that's the coal dust that's present. And so there has been long-running research trying to show the impact of coal in Curtis Bay and trying to get CSX out of the area. It's been unsuccessful so far, but we are trying to kind of build up evidence and publish them to kind of make aware of the consequences. So this is the CSX coal site. Chris and his team has set up a low-cost sensoring network here. So there are 10 monitors. As you can see, they're numbered from 1 to 10. This study will focus on only 4 of them that are marked yellow because they collected more air pollutants. And then we don't get an understanding of what's going on inside the coal terminal because the CSX does not sort of release any information. So Chris's team put up a trail camera on top of a tree. So the trail camera it gets triggered when there is bulldozer activity inside the coal terminal. And so with that, bulldozer activity is being measured using the trail camera. Okay. So what we have in Curtis Bay is minute-level measurements of size-resolved particulate matter, black carbon, carbon monoxide, nitrous oxide, nitrogen dioxide at 10 locations in Curtis Bay. We also have trail camera-based monitoring of bulldozer activity in the coal terminal, and we have other meteorological variables. Okay. So the first work we did was just looking at association of downwind and bulldozer activity with elevated air quality levels. And we pretty much found that for all of the major pollutants, you see an elevation in concentrations when there is ongoing bulldozer activity, and that elevation is sort of accelerated when it's downwind, when a site is downwind to the coal terminal. So this was published last year in Air Quality, Atmosphere, and Health, and it actually gained a lot of press attention. So as you can see, there's a lot of press published about it, and then after 1 week later, we saw this news coming out that the state of Maryland will. There is already a windscreen and part of the site, but a windscreen doesn't do much. But they will put up a bigger windscreen. We're trying to assess whether the windscreen does at all make any difference or not, but at least it's some step towards like the right direction. So that was the first part, which was kind of understanding if activities in the coal terminal are associated with elevated pollution levels. The second part was about trying to attribute the elevated pollution levels directly to the coal terminal, and that's sort of the idea of source apportionment. So essentially, from the sensors, we only get the pollutant levels, not where they came from. And pollution is coming from various different sources. There is like background regional sources, traffic, industry, and so on. And the measurements you're seeing are sort of a sum total of contributions from each of the sources. So source apportionment is essentially this deconvolution or unmixing problem where you take the concentrations and trying to break it up into parts that are coming from each of these sources. Right? So mathematically, what we have is we have this data matrix, Yij, where I stands for the time point, J stands for the pollutant. And then each of these measurements are a sum total of contributions from various sources. So you can break down Yij as sum total of contributions from K sources. And you can do a further breakdown that this Kth source, 1 unit of the Kth source produce this much of a particular pollutant, that is HKJ. And then at time point I, the Kth source produced this amount of units of pollution, essentially. So H is essentially the source profile, which says this source emits this type of pollutants, and then W is the source intensity or the source strength, which says at this time, this source was active very much or was not active, and so on. So this can be expressed in this form, Y equals to WH. H is the source profile matrix, W is the source strength matrix. As concentrations are all non-negative, this is essentially a non-negative matrix factorization problem. And there has been a lot of attempts to solve this, but the challenge is you only observe Y, and you're trying to infer on both W and H, and that is a fundamentally ill-posed problem. There can be multiple different Ws and H that give you the same Y. So you are not going to be able to get a unique solution. So different source apportionment methods addresses it in different ways. Chemical mass balance uses kind of known source profile, so H is known, so your only unknown is W. Positive matrix factorization, which is one of the most popular tools, it has sort of a tuning parameter which can make the solutions more sparse or more diffused, and then depending on your knowledge of the problem, you kind of figure out what's the interpretable solution is for your setting. Then there is also generic NMF software in R or Python, which you can add a lasso penalty or a ridge regression penalty. And then Jenna Kroll and Howard Chang has a very nice review paper on this. A less common perspective for source apportionment is to look at it in terms of geometry. Instead of solving this non-negative matrix factorization, there is an alternate and sort of somewhat niche point of view that you look at the geometry of the problem. And this is done by looking at the ith row of the data matrix Y, and it can be written in terms of a non-negative linear combination of the rows of the matrix H. And this sort of equation is a geometric shape. It's essentially what is called a simplicial cone, which is generated by non-negative linear combinations of a bunch of vectors. So that geometric shape is called simplicial cones, and the vectors that are generating this cone are called the extremal rays, or essentially the corner lines of this cone. So visually, this is what it looks like. So if you have the 3 rows of H, they will form a cone, and each data point that you're getting is a non-negative linear combination of the H. So they will lie in the cone that is generated by directing these 3 red lines. And the 3 red lines are the corner lines of the cone, or the extremal rays. So the idea of geometric NMF is that if you have enough data, you can identify the shape of the cone. And to kind of get an intuition, if you sort of look at the cross-section, you are essentially getting this bunch of dots, and you're asked to estimate a triangle. And if you have enough of these dots, the shape of the triangle becomes clearer and clearer, and you can draw a triangle which roughly approximates the true triangle. And then the corners of the triangle give you the H matrix up to some scaling and permutation. And there has been a lot of early work on this. Henry, 1997, had this method called unmix, which essentially does this idea, although he doesn't explain it in terms of simplicial cones. But this method is rarely considered as in source apportionment literature. As you will see in that review paper, they just talk about it in one line, saying that none of the modern computing software has an implementation of this. More generally, in NMF, there is work on geometric identifiability by David Donahoe in 2004 that was more focused on imaging applications, which is discrete data, and it requires the data to be exactly sparse, like having exact zeros, which is not true for air pollution. And it was more of a fixed matrix factorization problem, not sort of a probabilistic sampling frame where you have a generative mechanism for your data, use it to kind of make inference about the problem. So what we did here was we introduced a sampling framework. We say that the source intensity is a spatiotemporally dependent process, which is typically what it is. Like if a coal site is operating, the amount of sort of dust it is creating is a function of space and time. If there is traffic going on, the traffic-related air pollution is sort of a function of space and time. So we have a spatiotemporally dependent source intensity process, W, with some mean mu. And if we have that, the expected contribution from the kth source to the jet pollutant can be written as this product. And then the percent contribution is simply this product by sum over the same terms across all the sources. And so this gives what is called the percent of species in source apportionment literature. So for each pollutant, this is a percentage, and across all the K sources, this adds up to 100%. So it kind of directly gives you what percentage of a pollutant is coming from which source. So our recommendation was not to look at the individual factors, which we know are not identifiable, but look at this matrix. It is identifiable even if the individual factors are not. It is scale invariant, and it can be calculated unambiguously. And the algorithm to do it is fairly simple. What we do is we calculate the sample hull of our point cloud, and that will approximate the true cone. And you can show that it's sort of, as we get more and more data, the shape of the hull becomes very similar to the shape of the true cone. Then we take the K points in the hull, which maximizes the volume of the cone, and that gives you a sort of a close estimate or consistent estimate of this H matrix up to some scaling, and then you can solve for the mean vector mu using the NMF factorization. So I won't go into the details, but we could show that as you get more and more data, you can essentially, from the point cloud, you can identify the corners of the cone and solve the percent of species matrix. And this is actually a mechanism that benefits from having big data, as opposed to some of the other source apportionment software, which often don't work well for big data. Yeah.
Will this be a unique matrix for each sample site or each sensor?
You can do it separately for each sensor. We sort of stacked all the data together, but you can also do it separately. Yeah, because it's such a small region, so we stacked all the data together, but it can be done separately as well. So coming back to the Curtis Bay data, we had 500,000 one-minute records of 8 pollutants. And the minute level data is important because you have more data to fill up the point cloud. And then the short episodes like a cold terminal event can be detected by a minute level data that cannot be detected by hourly data. And these are the source apportionment results. So we identified 3 sources. The middle one, source 2, and this is all my collaborators' knowledge, this is not my knowledge, had a lot of the nitrous oxide, nitrogen dioxide, carbon monoxide, and they said this is most likely a traffic profile related to traffic. The first and third ones were related to coal terminals, partly because the first one has around 25% of black carbon, and a lot of the fine particulates. And the third one just picked out the total suspended particles, the coarse particulates. Then we did some post-hoc analysis. We looked at these intensity time series that were estimated and regressed them on the bulldozer activity and downwind. And we saw that source 2 does not have any association with downwind, but source or with bulldozer activity, but source 1 does. And source 3 has only association with the interaction of downwind and bulldozer activity. And we also looked at the diurnal pattern of the intensity of source 2, which had this distinct weekend and weekday structure, which further confirmed that it's most likely dominated by traffic contributions. And then for one particular day, there was a report filed by the company that their bulldozer got stuck in their coal mountain. And it was stuck for a couple of hours, and it generated a lot of coal dust. So we looked at the intensity profiles for that day. So the red is that the couple of hours that the bulldozer got stuck. And the black is the same set of hours for the next day and the previous day. This is the closest location where there is a sensor. This is a further away location. So you could clearly see that for the closest location, you saw a huge spike in concentrations. It was also picked up by our source 1 and source 3. Not so much in source 2, although there was some elevation as well. But in location 8, which was further away, the effect was much more moderate. There was only a mild spike, which kind of, again, gives more evidence towards how this source is related to possible coal site activity, because we saw a clear spike when we know that the bulldozer got stuck. So these are the references for this work. Both the geometric source apportionment method and its application are on arXiv, and then the first regression analysis has been published. In the interest of time, I will skip the third part, which was more on foundations of geospatial AI, which was led by 2 of my former students, Orko and Wentao. But I'll just give you the gist that there is a lot of use of machine learning and AI in environmental sciences, and taglines like this are super common, that artificial neural network models are superior compared to multiple linear regression for air pollution spatial forecasting. So I started doing this work maybe 6 years ago, kind of getting frustrated at taglines like this, because spatial data has unique features. It has spatiotemporal correlation. And from what I understood, none of these methods explicitly account for it. And so I'll skip this slide. But if you look at how, say, this is random forest, how random forest works, this is the blue line is the true nonlinear relationship between X and Y. The green line is the estimated relationship when there is no spatial correlation. The orange line is the estimated relationship when there is spatial correlation. So it clearly doesn't work as well when there is spatial correlation in the data. And we understood this both empirically and theoretically why it happens. And the takeaway message is, if there is spatial correlation in the data, your machine learning method should account for that spatial correlation. And how we do that, we have 2 papers out, one on random forest using generalized least square and one on neural networks. They have also softwares, but this is how they perform. So when you have correlated data and you use the random forest that accounts for spatial correlation, you get this maroon line. It aligns with the truth much more closely. So these are the papers for that, and we also have software for both of these methods. So if you're interested in trying this out, please do and send me feedback. And I have an open short course on machine learning regression. So if you're interested, you can find all slides, code, and data there. I'm also teaching the short course at JSM or the Joint Statistical Meetings this year, and also at the Environmental Statistics Conference in Houston later this year. Thank you.
About the exciting talk and all these very exciting topics. Any questions from the audience? Yes.
Yeah, thank you for your talk. Very nice overview of a lot of topics and getting into depth on some. A couple of points. You assume that the reference monitors are error-free, which is definitely not the case.
Yeah.
And also, they switched over technologies from mass-based to optical-based
Right.
in the time frame of your Baltimore data.
Right.
And that was done because you could get hourly data and it didn't require so many visits.
Right.
But the errors are different.
Right. Yeah. So yeah, definitely they are not error-free. We are more taking them as gold standard. So what we are predicting is sort of what these monitors would predict if they were at all the low-cost locations. That itself will have some extent of error, and we acknowledge that. And whenever I talk to Kirsten and my environmental health coordinators, they're like, that's a whole can of worms, and that's their own
But to
thing.
switch over to applications here, if I could interrupt.
Sure.
The apportionment is really important because we have compliance issue if EPA maintains a 9 microgram per cubic meter annual average standard. And it's really important to understand local gradients and things that drive that. And your application for the source apportionment is related to this one location in Baltimore?
It's a one neighborhood, but it has 10 network sites in that neighborhood. So it's very localized, yes.
Right, but what does the reference monitor say about compliance with the 9 microgram per cubic meter standard?
So the reference monitor is in a different part of the city. So it doesn't directly inform that neighborhood. But I think Baltimore overall has around 8 micrograms per meter cube average. So typically within the average, I know it was lowered from 12 to 9, I think in the last couple of years, the threshold. So I don't remember seeing like a violation information, but yeah, to double
So
check.
here in Detroit, we don't maintain that. We're about 10 or 11.
Mhm.
And so there's, at the national level, groups that are doing source apportionment for industry and saying that most of the differential is caused by commercial cooking and wood burning locally. And I think they've done it for Baltimore's.
Okay.
And so when you have one big source, like you say, traffic, it really embellishes a whole bunch of different sources.
Yeah. So that's why we didn't tag these sources as specifically coal or traffic. We said that I think traffic is contributing to this source because I think like the true pollution is a combination of so many different factors. So we wanted to be very careful about the wording here. Yeah, I agree with you. I do think that some of the things we saw in Curtis Bay, like dust, having like such a strong profile, that's not very common in other parts of the city. And so I think the consensus from the team was this is very likely from the coal side, especially we see it more elevated at the sensor just next to the site than the sensor a little bit further away. But again, like we don't know the truth, so we're just accumulating evidence and hopefully that will be kind of taken into heed. But, yeah. And just to go back about the change in measurement technology, I think the Baltimore instrument has been FEM throughout. I don't remember it changing during the time period of this.
Yeah, it's FRM.
Or FRM, okay.
The Federal Reference Method.
Yeah.
But the technology changes in the FRM.
Okay. I think this was a BAM, and it has stayed a BAM for a while. Yeah. Thank you.
Thank you. So I know we all have some other questions for the speakers, but because there's another class right after us, but we will open the floor for the lunch and poster section, and then our speaker will be there. So feel free to ask questions and continue all the conversations there. So it is going to be in the room 1680. Okay, so we'll see you there.
Thank you so much.